Very good morning to everyone. So today we will discuss a new topic, that is the spectroscopy for structural analysis. Now you can follow along as I display on the screen about this topic. Okay, so what is spectroscopy and why it is important, especially for organic chemistry? Spectroscopy is a method where you can elucidate the structure of molecules, so it's quite useful. Okay, so before we go into that, let's have a look at one important thing, that is the energy, which is the electromagnetic radiation. Okay, so what is the electromagnetic radiation? I'm sure you have come across these things like the X-rays, the ultraviolet rays, then the radio waves, and then we have also the radio waves. Now all these you must have come across in your life, like for example X-ray in medicines, ultraviolet rays, where if you are exposed to it you'll have skin burn or sunburn. Then we have the radio waves, which is widely used for mobile phone communications and also for radio communications. Then the radar waves, which is mostly used by military for communication, are in fact of course the last one, which is something we sometimes overlook, that is the visible light. Visible light is everything we see, the colors, the light, all these are visible light. Okay, now we have the all of these, they are all the electromagnetic radiation. Okay, so there's just different form of electromagnetic radiation which you encounter in different ways. So why is it important to study about this? So all these different kind of electromagnetic radiation or different categories, they interact with molecules differently. Okay, by now you must have learned about the dual nature of the electromagnetic radiation, and they can be wave nature or they can also be particle. So you can define it as it is a wave occurring simultaneously in the electrical and magnetic field. That's why the term electromagnetic radiation. It can also be described as if it consisted of particles called quanta or photons, like for example the quantization of energy and also photoelectric effect that you have seen. Photoelectric effect is also a way where you can describe electromagnetic radiation in the form of a particle. In spectroscopy, we are going to see electromagnetic radiation interact mostly in the form of a wave. Now let's have a look closely at the wave nature or the wave-like propagation of an electromagnetic radiation. It can be characterized either by wavelength, okay, or it can also be characterized by another property, that is by frequency. Okay, when a wave travels, it forms this kind of pattern where you have crests and you also have troughs. Okay, so this part is known as the crest and this part is known as the trough. Okay, so a complete cycle from crest to crest, like in this case, it is called as the wavelength or the distance or the length of the wave, or maybe from trough to trough like this, or it can be from any two different distance like in this case also. Okay, so all these are called as the wavelength. Now frequency, on the other hand, it is defined as the number of complete cycles per second. I mean, how many cycles it complete in 1 second. Like say for example, if suppose this is the distance, so this is 1 second. Okay, so how many cycle? 1 cycle is like 1 wavelength. 1 cycle is like 1 up and 1 down, that is 1 cycle. Okay, or 1 crest and 1 trough, that is 1 cycle. So if suppose from here to here is about 1 second. Okay, now if you have a short wave length, okay, short wavelength, you'll have many cycles in 1 second. Okay, if you have longer wavelength, you have shorter amount of cycle in 1 second. So just for differentiating, let's see, shorter wavelength, you have more cycles in the 1 second time frame. Okay, so these two, you can consider them to be related to one another, the frequency of radiation and the wavelength, they are related, or you can call us inversely proportional to each other. Okay, so let's have a look at this equation where we define the relationship between wavelength and frequency. So frequency here is inversely proportional to the wavelength, or it is equal to c by lambda. Okay, now c here is the speed of light, or the speed of electromagnetic radiation, and it's approximately about this value, 3 into 10 to the power 10 centimeters per seconds. Of course, what we can understand from here is that the shorter the wavelength, the higher will be the frequency, or more cycle can be completed in 1 second. The longer with the wavelength, then the smaller will be the frequency value. Now let's have a look at the relationship which Planck gave us, that is, the energy is related to frequency. So this define the what you call as particle nature of a wave. So energy is related to frequency. If the frequency is high, the energy also is high. That's why we see that high energy radiation and low energy radiation. And h here is a Planck constant. So then we can relate also the energy with respect to the wavelength by this equation, okay, where E equal to hc by lambda. So now here what we get is that as the wavelength becomes shorter, the energy become higher. When the wavelength is longer, the energy is lower. So let's just have a look at this electromagnetic spectrum. So spectrum means the whole electromagnetic spectrum, from the long wave spectrum to the short wave spectrum. So short wave in this case I've given on my right side, which will be on your right side also there, and the longer wavelength will be on the left side. Okay, so the first line here indicates if that particular frequency could penetrate the Earth's atmosphere or not. So you can see these, they could not penetrate. Okay, they could not penetrate. They are protected mostly by ozone layer. Then the visible light, infrared, that's how we get the warmth of the sun, it's from the infrared. Then the microwave does not, and then we have the radio wave. Okay, so this is just how which of these waves can penetrate the Earth's atmosphere. Now the radiation type. Okay, so we have different here. The longer wavelengths are called as radio. Then we have the microwave. As you go to shorter ones, then infrared, visible, UV, X-rays, and the gamma rays. Okay, now if you look at the scale, approximate scale of the wavelength, radio, they are of the order of a building. Okay, then somewhere in between radio and microwave, they have the length, or the length of the wavelength is around a human size. Then microwave is around a butterfly. Infrared is around a needle. Okay, Then the visible is around the microorganism. This is the length, the wavelength, or the measurement of the wavelength. Then as you go to shorter and shorter wavelength, they are the size of a molecule. Now it goes into nanometers. Okay, the size of the atoms and the size of the nucleus. Okay, then we have the fourth line here, which is the frequency. So wavelength here and frequency here. As you can see, when the wavelength is long, the frequency is also small. It's only 10 to the power 4. But when you go to the wavelength which is very short, frequency is of the order of 10 to the power 20. So now let's have a look at a simplified version of this one, of the electromagnetic spectrum. So the electromagnetic spectrum, as frequency increases, the wavelength decreases, and when frequency decrease in this direction, wavelength increase in this direction. In spectroscopy, different sections of the electromagnetic radiation interact differently with molecules, which give us valuable information. Like for example, the X-ray give us the X-ray diffraction, which ultimately can lead us to the structure of a molecule. Okay, then the UV visible, the UV and visible region mostly give us the what gas on saturation in a molecule. IR would give us the different functional group, and then the radio wave or the radio frequency give us information, very important part especially for organic molecules, because it gives us the nuclear magnetic resonance or NMR. Okay. Now if we look at these different regions of the electromagnetic spectrum, we can see here the wavelength. These are in nanometers, and then frequency are quite high, and we can see also the energy also is very high, of the order of 35. See, even visible region is of the order of 35.7 to 71.5 kilojoules per mole. In the UV region, they are of the order of 71 or higher in energy. The far UV can go up to 1900 kilojoules per mole. So these are very high energy radiation. But as you go to the IR region, they are in micrometer, not in nanometer anymore, and the energy is lower. Okay, frequency also is lower. Then the radio frequency or microwave energy also again here becomes lesser and lesser. Okay, so these are the different regions of the electromagnetic spectrum. Okay, so we'll wind up here for today, and in the next class we will talk about absorption spectroscopy, how molecules absorb electromagnetic radiation, and also how they also emit electromagnetic radiation.